Okay, and we're back. We're doing some mechanics, and it's a type of problem that I like to call relative motion problems. This is the kind of thing where you have multiple objects moving at different speeds, different directions perhaps, and it's the way things look and the speeds that you see things moving at could actually be different for different people from different points of view, or what we call frames of reference. A real good example of this would be what the different people see if you have two drivers in two different cars and you have maybe yourself standing on the side of the road at rest, and these cars are zooming by you, one at 50 miles per hour, one at 40 miles per hour. If you're just watching these cars, you just measure them at their 50 miles per hour and 40 miles per hour speeds. Okay, if let's say that the two cars are driving to your right, think about what the drivers see. The drivers, to them, they're at rest. Like if you're in a car, you think you're at rest, and you look out the window and you see the world moving past you at 50 miles per hour or 40 miles per hour in the other direction as to what the person on the side of the road sees you moving. These can tend to be confusing to a lot of people as you try to put your mind and try to get the point of view from different perspectives. If the cars are moving in the same direction, for example, individually they're still moving at 50 and 40, but let's say if you're a driver in the car, or if you're watching from the side of the road and you measure the speed at which the two cars are separating, if they're in the same direction, they only separate at 10 miles per hour. And one driver, if you're in the car going 40 miles per hour, you see the car going 50 moving past you at only 10 miles per hour. You wouldn't be able to tell that they're moving at 50, for example. Now, if the two cars are moving towards each other, the person on the side of the road, they see the closing speed would be equivalent to 90 miles per hour at which the two cars are approaching. Or if the two cars start back to back and they drive away from each other, they separate at 90 miles per hour. Okay, the combined speeds. So there's all sorts of weird scenarios you can think of. The example I want to do, though, is a kind of a classic. It's a vector problem. All of these are vector problems. And we're talking velocity vectors now, but this is something like if you're in a boat and you want to try to get to the other side of a river. Okay, so you want to just kind of steer your boat going straight across. The trouble is the river's also moving, but in a different direction. Okay, so it's a little different from the car example that we just mentioned. So the river, it's going to hit you. It's going to hit your boat sideways, and you want to go straight across. And you kind of know just from common sense that if you don't really do anything, the river is going to push you on a path that's angled. Okay, you're going to be pushed downstream compared to if you want to go straight across the river. So instead of ending up over here, you might get, by the time you get to the other side and the river's pushing you, if you don't do anything to correct it, you might be pushed all the way down there somewhere. Okay, so one of the questions becomes, well, how far do you actually get pushed off course if you don't make any corrections? If you just point the boat straight ahead to go across the river and you don't do anything? This is a vector problem. Okay, and it's actually not so bad once you kind of get the hang of it and understand what's going on here. You can take your boat's velocity, let's say it's 8 meters per second. So that, the 8 meters per second represents the fastest your boat can go in still water. Okay. But now the trouble is, you have a second velocity vector, the river, hitting you from the side going 5 meters per second. Where does the boat actually go? We can actually figure it out. We can calculate this. If you make a box with those two velocity vectors, the net velocity and the actual direction that the boat's going to move is that green line right there. It's splits that box in half. And suddenly you have these two right triangles. We could figure out the angle that we're getting misdirected. We could figure out the total speed if we wanted to. Okay, it becomes a right triangle problem. So for example, we could find out how far, or the angle that we're being pushed off course. If we do some basic trig, notice if we use one of these triangles, we could do, say, an arctangent or an inverse tangent. Let's see, so tangent is opposite over adjacent, so 5 over the 8. And when you punch that into your calculator, you get something like 32 degrees. And that's with respect to that vertical line. So you're being pushed off course at 32 degrees. This would be east of north, if you go ahead and use that kind of notation. We could use Pythagorean theorem and figure out what the net velocity, or that total velocity, is. Okay, that diagonal line. And the Pythagorean theorem will give you something like just under 9.43 is what I got, meters per second. Okay. Okay, so now what you could do is you could figure out some other things. The speed at which you're actually moving across the river is that 8 meters per second. And if we know how far the river is from bank to bank, let's say it's 50 meters, we could actually figure out how long it would take you to get across. Okay, so you're moving at a constant speed of 8 meters per second straight across the river. Now this is true whether the river is at rest or moving. Okay, if it's perpendicular, it's not affecting that 8 meters per second you're going across. So time is distance divided by speed. So the 50 meters divided by 8 meters per second. It would take you about 6 1/4 seconds to get across. Well, we could figure out now that we have the time that you're going across the river, and we know how fast the river is pushing you sideways off course, we could actually find out the distance you're getting pushed off course. Okay. Now distance is speed multiplied by time. Well, the horizontal speed is the 5 meters per second of the river, and it's pushing on you for 6.25 seconds. Okay, so if you were to go ahead and we could multiply that out and get something like a little over 31 meters away. Okay, so that's how far down the river you'd be pushed if you didn't make any corrections. Okay, well that's kind of a drag because you want to get straight across. What can you do? Well, here's the trick. To really go straight across, you have to negate what the river's doing to you. Okay, so let me keep all of this here, and let's see what the correction is. Okay, on the picture, what we have to do is you actually have to angle the boat into the river, so to speak. Now you can still move 8 meters per second, but you want to angle the boat a little bit. Why do that? Here's the key. What you want to do is you know how fast the boat can go. The fastest it can go is that 8 meters per second. Now we're going to angle it. What you want to do, though, is you want to negate the river, which is going to the right. And we know that velocity is 5 meters per second. If you could get your x component, your x velocity, to be 5 meters per second the other way, to the left, now you're in business. Okay, so we're going to make that right triangle. And remember, we want to go straight across the river, so we have to know what angle do we have to kind of tilt the boat at in order to go straight across. Well, that tilt has to give you an x component of 5 meters per second. So based on my picture here, our total speed, 8 meters per second, multiplied by the sine of the angle that I drew, that has to be equal to 5 meters per second going to the left. And that will negate, that'll cancel out the 5 meters per second that the river's trying to push you the other way. We can solve, using some basic trig, we can do an inverse sine of 5 divided by 8, and that'll give us how much we have to tilt the boat. That's something like 38.7 degrees. And on our picture, that would be west of north. That'll give you a horizontal speed of 5, which cancels the river. Notice you have another side of the triangle here, your y velocity. Let's figure that out. That side is going to be your hypotenuse, or 8 meters per second total, multiplied by the cosine of this angle that we just found, 38.7 degrees. If I were to calculate that out, that's a little over 6. It's about almost 6 1/4, 6.24 meters per second. That's the speed that's actually pushing you, making you travel across the river, straight across the river. The fact that you've negated what the river's trying to do to you sideways means that at 6.24 meters per second, that's going to get you across the river. How long is it going to take? Well, it's 50 meters divided by the 6.24. That's taking you across. And that's right at about 8 seconds. Okay, so instead of 6.25 seconds, if you didn't tilt the boat, it'll be added some time, 1 3/4 seconds, 8.0 seconds to get across. And you won't be, that's the key, you won't be pushed off course at all. You'll actually go straight across the river. Boats do this with ocean currents and river currents. Airplanes do this with air currents when they're flying, so they don't get pushed off course. Birds do this instinctively. On a windy day, you might actually notice at whatever direction a bird is flying, they might physically be tilted a little bit into the wind to negate the wind, and so they can fly, to whatever destination they want. But it's a vector problem. This is relative motion. Multiple things moving. How can we make corrections, in this case, for navigation purposes, so we don't get pushed off course? Okay, so hopefully this helps. This, again, is real common in physics classes at the high school level and beyond. And this is exactly what computers do now to navigate planes and boats and so on. So until next time, we'll see you later.